I go ahead and I open the sheet, and it's like, oh, it's here. Oh, I guess I already had it open. And I go to the start, it's like, well, table of contents, well, I haven't actually done this yet, but it's so chill, right? And then I go to, like, calculations, and it's like, whoa, what data set do you want to use? With, like a drop-down box that I coded in. And this reads data from, if I go to the very end, all of these data that I manually inputted, these are just, like, numbers. But it reads that data, right? And it uses that. And then I can be like, oh, do I want to use like the lower end of the data, or the mean, or the highest? I also have to code that in. The age group count, which is used for the calculations. And the species sex calculated in sex ratio, it's nothing too fancy. And like you can see, that these aren't actually all finished yet, so some of them say no type info stuff. No rounding, that's cool. So I don't round. If I do round, it's to the nearest whole number, or to the nearest 10th, or 100th, but that's fine. I'm just going to round to 0, and I'm going to calculate for 128 ages. That is so chill. Here's my elasticity. Basically, you remember those numbers that I had before that I showed you? In fact, don't look at all of the stuff on here. Just look at this. These are the numbers that I'm dealing with, right? Let's say I want to increase one of these by 100%. I want to increase the low survival rate of the young. Bam. I just do that. I can just do that right here for all the groups and for all the fertility rates, and I can change whether I'm increasing it by a percentage increase, or a multiple, or a flat value, and I coded that in, and I coded this in, and it's like, it's really cool, and I calculate to the decile, the centile, the millile, the 10,000th, the 100,000th, because there's actually no bile term for these. It just jumps to nanile, which is the thousandth, or the millionth, which makes sense. And then I calculate where I want to calculate elasticity for, which is something later, don't worry. And then, what my stabilized population growth is. So obviously, because this is a software to calculate population predictions. So if I have like one group, and then the next time, everyone who gives birth just gave birth. So the first group is going to have their population increase by like 9,000%, which is way out of line. But then obviously as that goes on and on and on, and populations die and live and give birth, and as that whole cycle continues, the population growth will stabilize to one number. That's a simplification. It never truly stabilizes, but for the purposes of this, let's just say it does. And right now we're doing that at age 128. Now, formatting, I haven't really done. Graphing, I've literally done nothing for. Custom dataset. Basically, if you don't want to use one of the datasets at the very start, like if you don't want to use one of the predetermined datasets, which I might add, are just the datasets we're given for the assessment. Like that just reads those, right? That's why you can see the freaking name change. Dataset 8 is a spare dataset that you can make yourself, or more interestingly, you can use a custom dataset. And now it'll just read from the custom values. So if I go to the custom dataset, if I go to the custom dataset, here, bam, this is the custom data. I input my own death rates, my own death rates low and high, fertility rates low and high, the measures for these, which again are coded in data validation boxes. Oh my god, if I can click it, it's pretty simple, right? Let's just go back to using dataset 1 mean, because that's the one I'm actually doing for my assessment. Value storage. Here's where the magic happens, right? In fact, let me just show you this freaking formula box, because this thing is beautiful. This thing really, really is beautiful. Now, if I go here, like that's a whole formula just for that, and for that, and for that, and for that, and it's fine because it's just, you can see where it changes. It's just changing which data measure it's reading. Same for here. I use let. I use a bunch of functions. It's really interesting. I do that for this as well, where I get rid of the amount of age groups I'm calculating. If I'm only calculating for 2 age groups, I only do 2. If I'm doing for 4, I do 4, such and such, and that's useful for what we do later. This is the final data that I'm using with the unadjusted data set, so the ones without those elasticity values I showed earlier. My initial population is 80, 36, 24, and 9 for the young adults, mature adults, and aging adults respectively. These are their respective survival rates. These are their respective fertility rates. Now, if I go and put this into what we call a Leslie matrix, which is just a big mathematical array for population predictions, I get this, where I have the final adjusted fertility rate, which is just the named range for this, and the final unadjusted survival rate along the subdiagonal, And then finally, zeros in every other corresponding square. And then I go, wow, wait, this is what the user inputted for elasticity. That's so cool. Anyway, if they chose to have it as a flat value, I just add it. If they choose it as a multiple, I use this formula, and if it's a percentage increase, I use this formula. And then that turns it into a value that I can apply specifically to the calculation. So I can go, wowie gee willikers, this is my new data. And you'll go like, whoa, this survivor is 0.4, but this one's 0.2. That's because it changed. It added 100% if you go back and look at the calculations. So looking at this matrix is different. That's a 0.4, that's a 0.2. Anyways, and then we have our elasticity values on the side. This is calculations for later. That's so chill. Anyways, applied elasticity calculation. Bam. This was a pain in the ass. Anyways, what I did here, to make it simple, is that I have like, survivor rates, fertility rates, and initial population for the base population. And then, do you remember way back here, you see how I can input something for all of these? Elasticity is a measure of how important that changes to the population growth rate. And here, I calculate every single one of these for every change I've been given. Here, the change came to 0.4. Everywhere else, there's actually no change, and that's why if you look at them all, they're all divided by 0 values, because you're just dividing at the end by the vital rate change, so it's 0. This one has a change. What do I do here? Well, I construct my Leslie matrix, which I could do more efficiently, and then I go and put this formula in. Matrix power. That doesn't look like an Excel formula. Oh yeah, because I went and manually coded in the formula. I manually coded in the formula. Like, I made the Excel formula. It was so fun, so horrible. I hated every single part of it. Yay! But what does this do? Well, Leslie matrices to the power of allow us to evaluate at a certain age. You remember way back when in the elasticity sheet when I had that popular growth consider choose where I was like, hey, how many ages do you want to calculate for? Well, I set that to 128, right? Anyways, matrix powers, the reason that this is so useful for Leslie matrices is because if I put the Leslie matrix for the initial population to the power of 10, and then multiply the Leslie matrix, the initial population matrix, by that matrix to the power of 10, it would give me the population at age 10. Leslie matrix to the power of n times the initial population is the population at age n, which is so cool, and it sucks that's not something natively supported in Excel, hence why I had to manually code it in. Anyways, that's super chill. This is just gonna let us shortcut right to age 128, and sure enough, if you look here, the population at age 128 for my normal population is 1.89 e to the negative 11. That means that before this one, there are 11 zeros in front of a decimal point. That is not good. I have like 1/billionth of a Bengal tiger. Doesn't count, unfortunately. Now, if we go here, we can look at the population prediction. Whoa, at age 128, these guys have like 418,000 tigers. Well, then I just apply the calculation of the original Leslie matrix to this population to get the next population. 446,000, right? Wow, then I can evaluate this and go, well, that population grew by 6%. It is a little higher than 6%, I would imagine. It's 6.359, but it visually rounds to 6%, not in the calculations, thank God. Now, crazy stuff, population growth change rate. What does this even mean? Well, you see here where my freaking population is decreasing by 26% every single age. This is what we call the stabilized population growth rate. Now, if I were to, for example, head back to elasticity and just go, actually, let me show this in a cooler way. Let me go to applied, view, new window, okay. You can see this sheet, right? And this sheet is the same sheet, it's just on a different window. If I were to change this value to 1, everything changes. You see these? Those are not all the same value. this value is drastically off of what it was before. In fact, it is, comically enough, just about double. We need to evaluate when this population stabilizes. So if you keep the number 26 in your head, it's not here, it's not here, it's not here, it's not... it's kind of here, right? Because I accidentally inputted 56, but if you go to like 18, okay, well we can go to like 15, or we can go to like... I didn't put the 15 in the right cell. You get the point, right? You can evaluate to whatever age count you want. And this was the cell I was inputting in. If I put in 1 here, these change back. If I put 128 in here, these go back to normal. Anyways, this is the stabilized population growth rate, which is why I have it named unadjusted population growth rate stabilized. I freaking love Excel. Now, I use this in my calculations. See, if these guys are growing by 6% every stabilized age, and these guys are dying by 26% every stabilized age, that means that the change I made to the vital rate, which was 100%, increased my population growth rate by 32%, 26 plus 6, or 6 minus negative 26 is the more mathematically correct way to do it. Anyways, the formula for elasticity goes, oh man, okay, well you can go bam, population growth rate divided by bam, vital rate change, and you can get 0.3222. That is just the same value as this because it's 0.3222 divided by 1, which is awesome. Fun fact, this formula for elasticity was on our task sheet and is literally made up. I fucking hate it. Anyway, that whole process is automated for each and every one of the possible vital rate changes for survival rate 1 and 2 and 3 and 4 and 5 and for the fertility rates, and you can see how they affect things. It's really interesting. Anyway, what the hell is going on here? Well, you see how before that took up like how many cells? Let's actually see. For my survival rate 1, it took 9 rows and 23 columns. 9 rows and 23 columns of working. I wanted to automate that, right? So I got this. What is this? It's just the same thing. Do you remember at the start of the last sheet we had the values for IP serve rate and fert rate? And those were adjusted by the percentage that you put into the elasticity sheet. Well, what if we didn't want it like that? What if we wanted to see how it changes every single 10% increase? Up to 200%. Or, more interestingly, what if we wanted to see how it changed every... Where's my mouse? Oh, I haven't fixed these ones. Okay, there's an error with this. It reads the wrong value. Ignore it. What if we only wanted to do that to 150%? That was a pain in the ass to code. You can actually look at the formula here. It's not too bad. It's pretty simple, but you can just see that jumps to way smaller than that. If I added like 2 zeros here, it would be so chill, and it fixes that, but I'll deal with that later. Anyways, what does this do? Well, this is the values I would use for survival rate and fertility rate for the survival rate 1. Just chill the flick out. Chill the flick out. Okay, what have I done? What have I done? Oh my gosh. Oh my gosh. Okay. These are those values, and then survival rate 1 is going to be affected by this percentage over and over and over and over again. And this happens for survival rate 2, and 3, and 4, and 5, and 6. Nope, fertility rate 1, and 2, and 3, and 4, and 5, and 6, and no number after 6. I trust you. Anyways, why is this sheet useful? Because of this. Shh, it's so beautiful. Basically what this does is it, you know, let's look at this one, right? This formula, it's so chill. This formula is your best buddy, dude. This formula probably pays for your lunch on a whim because he's a good, cool dude. Basically, remember that whole process of, we got the age 128 matrix, and the age 129, and there's a set, and multiply, and divide, and do a bunch of mathematical nonsense for a formula that doesn't exist. This does that in one formula. By creating the Leslie matrix in the formula, with a made-up formula that I fucking invented and I manually coded into Excel to work dynamically with different survival rates. And then using the matrix power formula, which again, I made up, and using the Leslie matrix formula, which again, I made up. Like, not made up as such, not as made up as the elasticity formula, but more so that I created, and then I just kind of do that over and over and over and over and over again, and this is the final elasticity if I change my population by 0%. Yeah, if I change it by 0%, there's zero change. What a freaking surprise. But if I change it by 10%, then for every percent it's changing, it's growing by 85%. That's crazy. That's fucking huge. And that's why they're color-coded dynamically based on what data is in this big square. And then what if I was like, oh, but I wanted to graph this? You've probably already seen it is graphed. Here's what the elasticities for survival rate looks like. That's the freaking blue. That's survival rate 1. And then that's survival rate 2. And then 5, and then 3 and 4 are probably also along the line of 5, because these values are pretty much identical. Probably something to do with the fact that they don't have a survival rate 4 and 5. Anyways, same thing for fertility rates, and then my interpreted value sheet is where all of this magic happens. This is the one user sees. Wow, base Leslie matrix, that looks so pretty. Elasticized Leslie matrix, that looks so pretty. Oh, here's a freaking color-coded graph, a table of which rates that I have are the most elastic, and you know what they are, and they're ordered, and it's so cool. And anyway, here's the elasticity rundown, which is going to be the same thing, except it's also going to do the top 5 for the survival rate and the fertility rate. I mean, each survival rate and each fertility rate, and then I go like, bam. My actual calculations for population aren't done, but I've done them in a prior sheet, and I just need to like work that formula over 60 hours.